Have you ever looked up at the night sky and wondered what it would be like to stand on the surface of Jupiter? Well, here's the thing that might blow your mind. You can't, because Jupiter doesn't have a surface to stand on. And even if it did, you'd be crushed by gravity so intense it would flatten you into a pancake thinner than paper. But that's just the beginning of Jupiter's mind-bending story. Tonight, we're diving deep into one of the most extraordinary questions in our solar system. How massive is Jupiter? And I mean truly, incomprehensibly massive. We're talking about a world so enormous that it challenges everything you think you know about planets. A cosmic giant that's more like a failed star than anything resembling the rocky worlds we're familiar with. If you've ever felt small looking up at the stars, just wait until you grasp the true scale of this gas giant lurking in the outer reaches of our solar system. Before we embark on this journey through the cosmic scales, I'd love to know where you're joining me from tonight. Drop your location in the comments below. There's something beautifully humbling about contemplating Jupiter's immensity while scattered across our tiny blue marble. Also, I would be grateful if you consider subscribing or hyping up this video with hype points if you like it. It would mean the world to me. Let's begin. Now, I want you to imagine something for a moment. Picture Earth, our entire world with all its oceans, continents, mountains, and cities. Got that image in your mind? Good. Now imagine you could somehow hollow out Jupiter like a cosmic jack-o'-lantern. You know how many Earths you could fit inside that hollow shell? Take a guess. 100? 500? Try over 1,300. That's right, you could stuff more than 1,300 Earth-sized planets inside Jupiter and still have room left over. But here's what makes this even more incredible. Despite being able to hold over 1,000 Earths, Jupiter is made almost entirely of the lightest stuff in the universe. Hydrogen and helium, the same ingredients that fuel the sun. This isn't just another astronomy video where I rattle off some numbers and call it a day. We're going to explore how Jupiter's massive scale has shaped our entire solar system, influenced the formation of life on Earth, and continues to act as our cosmic guardian. We're going to dive into recent discoveries that suggest Jupiter was once even larger than it is today, possibly twice its current size, with a magnetic field so powerful it defies imagination. By the end of this journey, you'll understand why Jupiter isn't just the biggest planet in our solar system. It's the reason our solar system exists the way it does. It's the heavyweight champion that threw its mass around during the early formation of our cosmic neighborhood, determining where planets could form and where they couldn't. It's a world so massive that it actually makes the sun wobble. But let's start with the basics, because even the basics about Jupiter are absolutely mind-blowing. When we talk about Jupiter's size, we're not just talking about something that's a bit bigger than Earth. We're talking about a scale so vast that it breaks our normal understanding of what a planet should be. Jupiter's diameter stretches across 88,846 miles at its equator. To put that in perspective, you could line up 11 Earths side by side, and they would just barely span Jupiter's width. But here's where it gets really interesting. Jupiter isn't perfectly round, because this massive world spins incredibly fast. Completing a full rotation in less than 10 hours, it's actually flattened at the poles and bulged out at the equator. We're talking about a difference of nearly 6,000 miles between its equatorial and polar diameters. That's like the distance from New York to London. Jupiter is literally stretched out of shape by its own rapid spinning. Think about that for a moment. This is a world so large that the difference between its equatorial and polar measurements is equivalent to crossing an entire ocean on Earth. And that difference exists because Jupiter is spinning so fast that centrifugal force is actually fighting against its own massive gravity to reshape the entire planet. Now, if Jupiter's diameter is 11 times larger than Earth's, you might think its volume would be 11 times larger too. But that's not how three-dimensional space works. When you scale up in 3 dimensions, the volume increases by the cube of the linear scale. This means Jupiter's volume is actually 1,021 times larger than Earth's. Let me help you visualize this. If Earth were the size of a grape, Jupiter would be the size of a basketball. But even that comparison doesn't fully capture the reality of what we're dealing with here. Because when we're talking about Jupiter, we're not just talking about size, we're talking about mass. And Jupiter's mass is where things get truly extraordinary. Jupiter weighs in at approximately 318 times the mass of Earth. But here's the kicker. If you took every other planet in our solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and all their moons, and somehow combined them into one superplanet, Jupiter would still be 2.5 times more massive. Let me repeat that. Jupiter alone contains more than twice the mass of everything else orbiting our Sun, except the Sun itself. This incredible mass concentration happened during the early formation of our solar system, about 4.6 billion years ago, when our solar system was just a swirling disk of gas and dust surrounding our newborn Sun. Jupiter began as a solid core of rock and ice in the outer regions, where temperatures were cold enough for these materials to condense. But once that core reached a critical mass, somewhere between 10 to 20 times the mass of Earth, something remarkable happened. Jupiter triggered what scientists call runaway gas accretion. It began vacuuming up hydrogen and helium directly from the solar nebula at an incredible rate. Within just a few million years, Jupiter had grown to roughly its current size, capturing most of the leftover material in the outer solar system. This process was so efficient and so complete that Jupiter essentially starved the rest of the outer solar system of building materials. That's why Mars is so much smaller than Earth, and why the asteroid belt between Mars and Jupiter never formed into a planet. Jupiter got there first and took everything. But Jupiter's mass isn't just impressive as a number on a page. It has real, tangible effects that we can observe and measure. Jupiter's gravity is so strong that it actually influences the orbit of the Sun itself. That's right. The Sun doesn't sit perfectly still at the center of our solar system. Instead, it wobbles slightly as Jupiter orbits around it. The gravitational interaction between these two massive objects creates a common center of mass called a barycenter that actually lies outside the Sun's surface. This solar wobble caused by Jupiter is so significant that astronomers use it as a technique for discovering planets around other stars. When they observe distant stars wobbling in a regular pattern, they know there's likely a massive planet, probably similar to Jupiter, orbiting that star. Jupiter's gravitational influence extends far beyond just making the Sun dance. It acts like a cosmic vacuum cleaner, protecting the inner solar system from potentially dangerous asteroids and comets. When these objects come careening in from the outer solar system, many of them get captured by Jupiter's gravity or flung out into interstellar space. Without Jupiter's protective presence, Earth would be bombarded by far more potentially extinction-causing impacts. The asteroid belt itself bears witness to Jupiter's gravitational dominance. Instead of forming into a planet, the rocky debris between Mars and Jupiter remains scattered in a belt because Jupiter's gravity prevents it from coalescing. Jupiter's influence creates gaps in the asteroid belt called Kirkwood gaps. where its gravitational resonances have cleared out material over millions of years. But here's something that might surprise you. Despite Jupiter's enormous mass, it's actually less dense than water. Jupiter has a density of only 1.33 grams per cubic centimeter, compared to Earth's 5.5 grams per cubic centimeter. This low density tells us something crucial about Jupiter's composition. It's made primarily of the lightest elements in the universe. About 90% of Jupiter's atmosphere is hydrogen, with most of the remaining 10% being helium. These are the same elements that fuel nuclear fusion in stars. In fact, Jupiter contains essentially the same basic ingredients as the Sun. The only difference is that Jupiter never quite reached the mass necessary to ignite nuclear fusion and become a star itself. Some scientists refer to Jupiter as a failed star, and there's truth to that description. If Jupiter had been about 80 times more massive, it would have had enough gravitational pressure in its core to start fusing hydrogen into helium. Instead of a planet of being in our solar system, it would have been a second sun, making our solar system a binary star system. This raises a fascinating what-if scenario. What if Jupiter had managed to accumulate just a bit more mass during its formation? Our solar system would look completely different. Earth might not exist at all, or if it did, it would be a very different world with two suns in its sky. The internal structure of Jupiter is as alien as its size is impressive. As you descend through Jupiter's atmosphere, the hydrogen gradually becomes more and more compressed. About a third of the way down, something extraordinary happens. The hydrogen becomes so compressed that it transforms into a metallic state. This metallic hydrogen doesn't exist naturally anywhere on Earth. We can only create tiny amounts of it in laboratory conditions for microseconds at a time. But inside Jupiter, this metallic hydrogen exists in vast quantities, forming what might be the largest ocean in our solar system. Not an ocean of water, but an ocean of liquid metal, thousands of miles through-lit hydrogen that extends for Jupiter's interior. This metallic hydrogen ocean is responsible for one of Jupiter's most impressive features, its magnetic field. As Jupiter spins rapidly on its axis, this conducting metallic hydrogen creates currents that generate an electrical magnetic field approximately 20,000 times stronger than Earth's magnetic field. The scale of Jupiter's magnetosphere, the region of space dominated by its magnetic field, is truly staggering. It extends millions of miles in all directions, reaching almost to Saturn's orbit on the side away from the Sun. If you could see Jupiter's magnetosphere with the naked eye, it would appear several times larger than the full moon in Earth's sky. This massive magnetosphere traps and accelerates charged particles to incredible energies, creating radiation belts that are millions of times more intense than Earth's Van Allen belts. The radiation environment around Jupiter is so harsh that it poses serious challenges for spacecraft visiting the system. The electronics on these spacecraft must be specially hardened to survive even brief exposures to Jupiter's radiation. The interaction between Jupiter's powerful magnetosphere and its moons creates some of the most spectacular phenomena in our solar system. The moon Io, orbiting deep within Jupiter's radiation belts, experiences tidal forces so intense that they heat its interior and drive constant volcanic activity. The electrical current flowing between Jupiter and Io generates more power than all of Earth's power plants combined. Recent missions to Jupiter have revealed that the planet's size and structure are even more complex than we previously understood. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has provided unprecedented insights into the giant planet's interior. The data suggests that Jupiter's core might be larger and more diffuse than scientists expected, extending over a significant portion of the planet's radius rather than being a small, dense nucleus at the center. These findings indicate that Jupiter's formation might have been more chaotic and violent than previously thought. Rather than smoothly accumulating material in layers, Jupiter might have experienced massive impacts and mixing events that created its current internal structure. But perhaps the most mind-bending recent discovery is that Jupiter might have been even larger in the past. Some calculations suggest that early Jupiter could have been more than twice its current size, with a magnetic field 50 times stronger than it is today. This massive early Jupiter would have had even more dramatic effects on the formation and evolution of our solar system. The idea of an even larger ancient Jupiter helps explain some puzzling features of our solar system's architecture. It might account for why Mars, the asteroid belt, never formed into a planet, is so much smaller than Earth, and why the outer orbital planets have the characteristics we observe today. As we continue our exploration of Jupiter's massive scale, we'll delve deeper into how this giant world continues to shape our solar system today. Examine the incredible atmospheric phenomena that play out across its vast surface, and discover how Jupiter's size compares to the most extreme objects in our universe. The sheer scale of Jupiter's atmospheric dynamics makes Earth's most powerful hurricanes look like gentle summer breezes. When we talk about weather on Jupiter, we're talking about storm systems that operate on scales our planet-bound minds can barely comprehend. The Great Red Spot, Jupiter's most famous storm, has been raging for over 300 years. That's longer than the United States has existed as a nation. This single storm system is 10,000 currently about miles wide, which means you could drop Earth into it and still have thousands of miles of storm left over. But here's what really puts Jupiter's atmospheric scale into perspective. The Great Red Spot is actually shrinking. When astronomers first began systematically observing it in the late 1800s, it was more than twice its current size, stretching over 25,000 miles across. Even as it shrinks, this ancient tempest remains larger than our entire planet. And it's not just a surface phenomenon. Recent measurements from the Juno spacecraft have revealed that the Great Red Spot extends over 200 miles deep into Jupiter's atmosphere. To put that in context, if Earth had weather systems that deep, they would extend well into what we consider outer space. The longevity of Jupiter's storms reveals something fundamental about the difference between gas giants and terrestrial worlds. On Earth, storms eventually dissipate when they encounter land masses, mountains, or other geographical features that disrupt their flow patterns. But Jupiter has no solid surface to break up its atmospheric circulation. Instead, its storms can persist for decades or centuries, drawing energy from the planet's internal heat and the complex interactions between different atmospheric layers. Jupiter generates more heat than it receives from the Sun. This might sound impossible, but it's absolutely true. The planet radiates about 1.6 times more energy into space than it absorbs from solar radiation. This excess heat comes from gravitational compression. Jupiter is still slowly contracting from its formation 4.6 billion years ago. And this ongoing contraction generates tremendous amounts of thermal energy. It's like a cosmic hand warmer that's been slowly releasing heat for billions of years. This internal heat source drives atmospheric circulation patterns that span thousands of miles. Jupiter's atmosphere is organized into distinct bands of clouds that circle the planet parallel to its equator. These bands, called zones and belts, are created by powerful jet streams that can reach speeds of over 400 miles per hour. The zones appear bright because they contain clouds of ammonia ice crystals high in the atmosphere. while the darker belts represent regions where gas is sinking deeper into the planet's interior. The colors we see in Jupiter's atmosphere tell a story of complex chemistry operating on a planetary scale. The browns, reds, and yellows come from organic compounds created when lightning and solar radiation interact with methane, ammonia, and other trace gases in the atmosphere. These chemical reactions produce molecules called tholins, which give Jupiter its distinctive appearance. The scale of this atmospheric chemistry is staggering. Jupiter's atmosphere contains trace amounts of water vapor that, when calculated across the planet's enormous volume, likely exceed all the water in Earth's oceans. Lightning on a scale that on Jupiter operates dwarfs terrestrial thunderstorms. Individual lightning bolts can be thousands of times more powerful than those on Earth, and they occur in regions where the atmospheric pressure is many times greater than at Earth's surface. The Juno spacecraft has detected lightning strikes that generate radio waves so powerful they can be detected from millions of miles away. These aren't just weather phenomena, they're electromagnetic events that influence the entire Jovian system. The rapid rotation that creates Jupiter's oblate shape also generates some of the most complex atmospheric dynamics in the solar system. Different latitudes rotate at different speeds, creating shear zones where adjacent bands of atmosphere slide past each other at hundreds of miles per hour. These shear zones become breeding grounds for new storm systems and help maintain the planet's distinctive banded appearance. But Jupiter's influence extends far beyond its own atmospheric boundaries. The planet's enormous magnetosphere creates a radiation environment so intense that it fundamentally shapes the characteristics of its entire moon system. The 4 largest moons, discovered by Galileo over 400 years ago, exist in a gravitational and magnetic environment unlike anywhere else in the solar system. Io, the innermost of the large moons, experiences tidal forces from Jupiter that are 7,000 times stronger than the tidal forces Earth exerts on our moon. These forces constantly flex and stretch Io's interior, generating enough heat to power over 400 active volcanoes across its surface. The volcanic plumes from these eruptions can shoot material over 300 miles high, creating a thin atmosphere of sulfur dioxide that gets stripped away by Jupiter's magnetic field and forms a donut-shaped ring of charged particles around the planet. Europa, the second of Jupiter's large moons, harbors what might be the largest ocean in our solar system beneath its icy surface. This subsurface ocean contains more than twice as much water as all of Earth's oceans combined. The ocean exists because Jupiter's tidal forces generate enough heat to keep the water liquid, despite Europa being much farther from the Sun than Earth. The scale of this hidden ocean is mind-boggling. It's estimated to be 40 to 100 miles deep, compared to Earth's oceans, which average less than 2.5 miles in depth. Ganymede, Jupiter's largest moon, is bigger than the planet Mercury and has its own magnetic field generated by a liquid iron core. The interaction between Ganymede's magnetic field and Jupiter's creates auroras at Ganymede's poles that have been observed by the Hubble Space Telescope. These auroras provide evidence for yet another subsurface ocean, this one sandwiched between layers of ice within Ganymede's interior. Callisto, the outermost of the large moons, is one of the most heavily cratered objects in the solar system, bearing the scars of billions of years of impacts. Its surface is so ancient and battered that it provides a window into the early history of our solar system, when the planets were still forming and debris was much more common. The scale of the Jovian moon system becomes even more impressive when you consider the smaller moons. Jupiter has at least 79 known moons, and more are discovered regularly as our telescopes become more sensitive. Many of these smaller moons are likely captured asteroids, snatched from their original orbits by Jupiter's immense gravitational pull. Some of these tiny moons have such eccentric orbits that they take years to complete a single trip around Jupiter. The gravitational interactions within the Jovian system create a complex dance of orbital mechanics. The three inner large moons, Io, Europa, and Ganymede, are locked in what's called a Laplace resonance. For every orbit Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise mathematical relationship helps maintain the orbital stability of the system and contributes to the tidal heating that drives geological activity on these moons. Jupiter's role as a gravitational shepherd extends throughout our solar system. The Trojan asteroids, 2 groups of rocky bodies that share Jupiter's orbit around the Sun, provide evidence of the planet's long-term gravitational influence. These asteroids occupy stable gravitational zones called Lagrange points, located 60 degrees ahead of and behind Jupiter in its orbit. There are over 7,000 known Trojan asteroids, and they represent material that has been gravitationally captured and held in place by Jupiter for billions of years. The influence of Jupiter's gravity reaches even further into the outer solar system. The planet acts like a gravitational gateway that determines which comets from the distant Kuiper belt and Oort cloud make their way into the inner solar system. When these icy bodies venture too close to Jupiter, they can be either ejected from the solar system entirely or redirected into new orbits that bring them closer to the Sun. Some of the most spectacular comets visible from Earth owe their trajectories to gravitational encounters with Jupiter. Comet Shoemaker-Levy 9 famously collided with Jupiter in 1994 after being torn apart by the planet's tidal forces during a previous close approach. The impact created explosion sites larger than Earth and provided astronomers with a dramatic demonstration of Jupiter's role as a cosmic protector, absorbing impacts that might otherwise threaten the inner planets. The scale of Jupiter's protective influence becomes clear when you consider the statistics. Computer simulations suggest that without Jupiter's gravitational presence, Earth would experience impacts from large asteroids and comets at rates hundreds of times higher than we actually observe. These impacts could have prevented the development of complex life or caused multiple mass extinctions throughout Earth's history. But Jupiter's gravitational influence isn't always protective. The same gravitational forces that can deflect dangerous objects away from Earth can also redirect them toward us. Some scientists argue that Jupiter acts more like a gravitational stirrer than a shield, sometimes increasing the impact rate in the inner solar system. The reality is probably somewhere in between, with Jupiter's net effect being protective, but with occasional exceptions. Recent discoveries of exoplanets, planets orbiting other stars, have given us new perspective on just how unusual Jupiter's size and position might be. Most of the giant planets discovered around other stars are much closer to their host stars than Jupiter is to the Sun. These hot Jupiters have orbital periods of days or weeks rather than Jupiter's 12-year orbit. The existence of these close-in giants suggests that planetary migration is common during solar system formation, raising questions about how Jupiter managed to end up in its current distant orbit. Some models suggest that Jupiter actually migrated inward toward the Sun during the early stages of solar system formation, before reversing course and moving back outward. This hypothetical journey, called the Grand Tack model, could explain many puzzling features of our solar system's architecture. If Jupiter had continued its inward migration, it might have disrupted the formation of the terrestrial planets entirely. The study of Jupiter's size and mass continues to reveal new insights about planetary formation throughout the universe as a natural. The planet serves laboratory for for understanding how gas giants form and evolve. Every new measurement of Jupiter's internal structure, atmospheric composition, or magnetic field provides clues about the processes that shaped not only our own solar system, but potentially countless others throughout the galaxy. As we push deeper into our exploration of Jupiter's massive scale, we begin to encounter questions that challenge our understanding of what it means to be a planet. At what point does a planet become so large that it should be classified as something else entirely? How do the physical processes operating within Jupiter compare to those in brown dwarfs, those failed stars that bridge the gap between planets and true stars? Jupiter exists at a fascinating boundary in the cosmic hierarchy of objects. It's too small to be a star, too large to be considered a typical planet, and too massive to ignore when considering the dynamics of our solar system. In many ways, Jupiter represents a category unto itself, a gas giant whose influence extends far beyond its physical boundaries and whose story is intimately connected to the story of every other object in our cosmic neighborhood. The more we learn about Jupiter's true scale and influence, the more we realize that understanding this giant planet is key to understanding our place in the universe. Jupiter didn't just happen to form in our solar system, it fundamentally shaped the solar system we inhabit today. The question of Jupiter's classification becomes even more intriguing when we dive into the cutting-edge discoveries about its interior structure. Until recently, scientists assumed Jupiter had a small, dense core surrounded by layers of metallic hydrogen and regular hydrogen atmosphere. But the Juno mission has completely revolutionized our understanding of what lies beneath Jupiter's cloud tops. What Juno found was shocking. Instead of a small, well-defined core, Jupiter appears to have what scientists call a fuzzy or dilute core that extends through nearly half the planet's radius. This isn't the neat, layered structure we expected. It's more like a gradual transition from rock and ice mixed with hydrogen and helium, stretching across tens of thousands of miles. Think about what this means. The core region of Jupiter is larger than the entire planet Earth, and it's not even a solid boundary. It's a transitional zone where the distinction between core and atmosphere becomes meaningless. This discovery suggests that Jupiter's formation was far more violent and chaotic than we previously imagined. The leading theory now is that during Jupiter's early formation, it suffered massive impacts from other planetary embryos, objects potentially as large as Earth itself. These collisions would have stirred up Jupiter's interior, mixing the rocky core material with the hydrogen and helium atmosphere. The result is the fuzzy core structure we observe today. But here's where Jupiter's story becomes even more mind-bending. The pressures and temperatures inside this giant world reach extremes that don't exist anywhere else in our solar system. About 7,000 miles below the cloud tops, the pressure becomes so intense that hydrogen transforms into that exotic metallic state. This isn't just a phase change like water turning to ice. This is hydrogen being squeezed so hard that its electrons are stripped away, creating a liquid that can conduct electricity like copper wire. The metallic hydrogen region extends for thousands of miles through Jupiter's interior, creating the largest volume of this exotic matter anywhere in the known universe. On Earth, we can only create metallic hydrogen for microseconds in the most powerful laboratory presses. Inside Jupiter, it exists in quantities that boggle the mind, forming vast oceans of liquid metal under pressures millions of times greater than Earth's atmosphere. This metallic hydrogen ocean is what drives Jupiter's incredible magnetic field. As the planet rotates every 10 hours, this conducting fluid generates electrical currents that create magnetic field lines stretching millions of miles into space. The energy contained in Jupiter's magnetic field is so enormous that if we could somehow harvest it, it could power human civilization for billions of years. But Jupiter's magnetic environment isn't just powerful, it's also incredibly complex. Unlike Earth's relatively simple dipole magnetic field, Jupiter's field has multiple poles and complicated structures that shift and change over time. Recent observations have shown that Jupiter's magnetic field is actually changing much more rapidly than Earth's, with some regions showing significant variations over just a few years. This changing magnetic field has profound effects on Jupiter's radiation environment. The planet traps charged particles in radiation belts that make the space around Jupiter one of the most dangerous regions in our solar system for both spacecraft and any potential future human explorers. The radiation levels near Jupiter are so intense that they would deliver a lethal dose to an unprotected human in a matter of minutes. The scale of Jupiter's magnetic influence extends far beyond what we can see. Radio telescopes on Earth regularly detect powerful radio emissions from Jupiter, created by charged particles spiraling along magnetic field lines at nearly the speed of light. These radio signals are so strong that amateur radio operators with basic equipment can detect them from Jupiter's orbit over 400 million miles away. The interaction between Jupiter's magnetic field and the solar wind creates a bow shock wave in space that begins millions of miles before the solar wind even reaches Jupiter's magnetosphere. It's like Jupiter creates its own weather system in the vacuum of space, deflecting and reshaping the stream of charged particles flowing outward from the Sun. When we talk about Jupiter's size, we often focus on its physical dimensions, but its magnetic presence makes it effectively much larger than its physical body. The total volume of space dominated by Jupiter's magnetic field is comparable to the volume inside Mercury's orbit around the Sun. In a very real sense, Jupiter's influence extends across a region of space larger than some planetary orbits. This magnetic dominance has shaped the evolution of Jupiter's entire moon system. The 4 largest moons all orbit within Jupiter's magnetosphere, subjecting them to constant bombardment by high-energy particles. Over billions of years, this radiation has darkened their surfaces and driven chemical changes in their atmospheres and surface materials. The radiation environment around Jupiter creates phenomena that exist nowhere else in our solar system. Io's volcanoes don't just spew lava and gas into space. They also inject charged particles directly into Jupiter's magnetic field, creating a torus of glowing plasma that orbits the planet at Io's distance. This plasma torus is invisible to the human eye but glows brightly in ultraviolet and radio wavelengths, creating what's essentially a 3,000-mile wide ring of superheated gas around Jupiter. The electrical connection between Jupiter and Io carries a current of about 5 million amperes, equivalent to the power output of dozens of nuclear power plants. This current flow creates aurora displays at Jupiter's poles that are hundreds of times more powerful than Earth's northern and southern lights. These Jovian auroras cover areas larger than Earth and shine with intensities that would be visible from space even during Jupiter's daytime. Recent discoveries have revealed that Jupiter's aurora are not only incredibly powerful, but also surprisingly variable. Unlike Earth's aurora, which are primarily driven by solar wind interactions, Jupiter's aurora are largely powered by the planet's own rotation and its interactions with its moons. The result is aurora displays that can persist for hours or days and cover enormous regions of Jupiter's polar atmosphere. The scale of energy involved in Jupiter's magnetosphere becomes clear when we consider that the planet's magnetic field stores more energy than the total kinetic energy of all the asteroids in the asteroid belt. This energy occasionally gets released in explosive events that send shockwaves throughout the Jovian system and can be detected by spacecraft throughout the outer solar system. Jupiter's rapid rotation, completing one full spin 9 every 9 hours, creates additional complications in its magnetic field structure. The centrifugal force from this rapid rotation stretches the magnetic field lines outward, creating a disc-like structure in the equatorial plane that extends far beyond the orbit of Jupiter's outermost moons. Material trapped in this magnetic disk gets spun up to incredible speeds, creating a population of charged particles moving at thousands of miles per second. The combination of Jupiter's size, mass, rotation, and magnetic field creates what scientists call a mini magnetosphere that operates like a scaled-down version of the entire solar system. Jupiter's moons orbit within this magnetosphere like planets orbiting within a stellar wind, experiencing conditions that are simultaneously familiar and utterly alien. But perhaps the most remarkable aspect of Jupiter's scale is how it continues to surprise us, even after centuries of observation. Every new mission to Jupiter reveals phenomena that weren't predicted by our models. The Galileo mission discovered that Jupiter's magnetic field is much more complex than expected. The Juno mission found that the planet's interior structure is completely different from what we thought. The James Webb Space Telescope has recently provided new insights into Jupiter's atmospheric dynamics, revealing temperature and chemical variations across the planet's surface that weren't visible to previous instruments. These observations are showing us that Jupiter's atmosphere is even more complex and dynamic than we realized, with temperature differences and chemical gradients that operate on scales spanning thousands of miles. One of the most recent discoveries about Jupiter's scale comes from studies of its gravitational field by the Juno spacecraft. These measurements have revealed that Jupiter's interior of different density is not uniform but contains regions that extend deep into the planet. These density variations suggest that Jupiter's formation involved processes we're still trying to understand, possibly including the merger of multiple planetary embryos during the early stages of solar system formation. The gravitational mapping has also revealed that Jupiter's core extends much farther from the planet's center than anyone expected. Instead of being a compact ball of rock and ice, Jupiter's core appears to be a partially dissolved mixture of heavy elements and hydrogen that extends across nearly 60% of the planet's radius. This means that the core of Jupiter is larger than the entire planet Saturn. These discoveries about Jupiter's internal structure have implications that extend far beyond our solar system. As we discover more exoplanets around other stars, many of which are gas giants similar to Jupiter, understanding how these worlds form and evolve becomes crucial for understanding planetary systems throughout the galaxy. Jupiter serves as our nearest example of a gas giant, a laboratory where we can study processes that probably occur around countless other stars. The more we learn about Jupiter's true scale and complexity, the more we realize that this giant planet represents a fundamental type of world that may be among the most common in our galaxy. Recent surveys suggest that gas giants like Jupiter may be present in a significant fraction of planetary systems, making Jupiter not just a local curiosity, but a representative of a major class of planetary objects throughout the universe. But Jupiter's influence on our own solar system continues to unfold in ways we're still discovering. Computer simulations of early solar system evolution suggest that Jupiter's gravitational influence may have prevented the formation of a planet between Mars and Jupiter, instead creating the asteroid belt we see today. Without Jupiter's presence, our solar system might have contained an additional terrestrial planet, fundamentally altering the architecture of our cosmic neighborhood. The same gravitational influences that prevented planet formation in the asteroid belt may have also played a crucial role in delivering water to Earth during the early bombardment period. Jupiter's gravity would have scattered comets and asteroids throughout the inner solar system, some of which would have collided with Earth, potentially providing much of the water in our oceans. As we continue to study Jupiter's massive scale and its effects on our solar system, we're beginning to understand that this giant planet isn't just a member of our cosmic family. It's more like the patriarch whose presence has shaped the characteristics and destinies of every other world in our solar system. From the asteroid belt to the outer reaches of the Kuiper belt, Jupiter's gravitational influence has left its mark on virtually every object that orbits our Sun. The study of Jupiter's scale also provides insights into the fundamental physics of planetary formation and evolution. The processes that created Jupiter, from the initial accumulation of solid materials to the runaway accretion of gas from the solar nebula, represent some of the most dramatic events in the history of our solar system. Understanding these processes helps us understand how planetary systems form and evolve around other stars throughout the galaxy. Jupiter's influence on planetary formation extends even deeper when we consider the timing of its growth. Recent computer models suggest that Jupiter reached its current size remarkably quickly in cosmic terms, achieving most of its mass within just the first few million years of our solar system's existence. This rapid formation had cascading effects throughout the entire solar neighborhood. During this early period, Jupiter acted like a cosmic bulldozer, clearing out vast regions of the primordial solar disk. The planet's gravity carved gaps in the disk of gas and dust surrounding the young Sun, creating zones where smaller objects couldn't accumulate into larger bodies. This gravitational clearing process explains why the outer solar system beyond Jupiter contains relatively few large objects compared to what we might expect. But Jupiter's early dominance created another fascinating phenomenon. As it grew, Jupiter began migrating inward toward the Sun, drawn by gravitational interactions with the remaining disk material. This inward migration could have been catastrophic for the inner solar system. If Jupiter had continued moving sunward, it might have scattered or destroyed the rocky material that eventually formed Mercury, Venus, Earth, and Mars. Fortunately for us, something stopped Jupiter's inward journey. The most likely explanation involves Saturn, the second largest planet in our solar system. As Saturn grew and began its own migration, the gravitational interaction between the two gas giants created a resonance that reversed their motion, sending both planets back outward to roughly their current positions. This gravitational dance between Jupiter and Saturn, known as the Grand Tack model, may have been the crucial event that allowed terrestrial planets like Earth to form at all. The scale of this early migration becomes mind-boggling when you consider the distances involved. Jupiter may have traveled inward to within the orbit of Mars before reversing course and moving back out to its current position beyond the asteroid belt. That's a round trip of hundreds of millions of miles, accomplished by an object with more mass than 2.5 Earths combined. Imagine the gravitational chaos this journey must have created throughout the early solar system. This migration scenario helps explain one of the most puzzling features of our solar system: why Mars is so much smaller than Earth. Computer simulations suggest that Jupiter's inward journey truncated the formation of Mars, preventing it from accreting additional material that would have made it a much larger world. Without Jupiter's gravitational interference, Mars might have grown in size to Earth, or to be similar, even larger. The implications of Jupiter's early migration extend to existence the very of life on Earth. If Jupiter had followed a different path, Or if its interaction with Saturn had played out differently, Earth might never have formed in the habitable zone around our Sun. The delicate balance that allowed our planet to develop liquid water oceans and a stable climate may depend entirely on the specific gravitational choreography that occurred between Jupiter and Saturn over 4 billion years ago. One of the most remarkable examples of Jupiter's long-term influence involves the orbital characteristics of asteroids and comets. Jupiter's gravity creates what scientists call resonances, specific orbital periods, where small objects experience regular gravitational tugs that can either stabilize their orbits or eject them from the solar system entirely. These resonances create a complex web of gravitational influences that extends throughout the asteroid belt and beyond. The Kirkwood gaps in the asteroid belt provide visible evidence of these resonances. These are regions where asteroids are notably sparse, cleared out over millions of years by Jupiter's repeating gravitational influence. An asteroid in one of these gaps experiences a gravitational tug from Jupiter at the same point in its orbit, gradually increasing the asteroid's orbital eccentricity until it either collides with another object or gets ejected from the belt entirely. The scale of Jupiter's gravitational reach becomes evident when we consider that these clearing effects operate over distances of hundreds of millions of miles. Jupiter doesn't need to be close to an object to influence its fate. The planet's massive gravity can gradually reshape orbits through accumulated effects that play out over millions of orbital periods. This long-term gravitational sculpting has profound implications for understanding impact hazards on Earth. Jupiter acts as both a shield and a source of potentially dangerous objects. While the planet's gravity deflects many comets and asteroids away from the inner solar system, it also occasionally redirects objects onto Earth-crossing orbits. The net effect appears to be protective, but the relationship is complex and continues to be studied by planetary scientists. Jupiter's gravitational influence also extends to the very edge of our solar system. The planet helps determine which objects from the distant Oort cloud, a spherical shell of comets surrounding our solar system, eventually make their way inward to become visible comets. When these distant, icy bodies are nudged by passing stars or galactic tides, their subsequent paths through the solar system are largely determined by gravitational encounters with Jupiter. Some of the most spectacular comets visible from Earth owe their current orbits to past encounters with Jupiter. The planet can capture comets into shorter period orbits, creating the family of Jupiter family comets that return to the inner solar system every few years or decades. Alternatively, Jupiter can accelerate comets to such high velocities that they're ejected from the solar system entirely, never to return. The scale of this gravitational influence becomes clear when we consider that Jupiter has been performing this cosmic traffic control for over 4 billion years. The cumulative effect of countless gravitational encounters has fundamentally shaped the population of small bodies throughout our solar system. Without Jupiter's presence, the distribution of asteroids, comets, and other debris would be completely different. Recent discoveries about Jupiter's moons have revealed another dimension of the planet's massive scale. The Jovian system contains at least 79 known moons, ranging from the 4 giant Galilean satellites to tiny captured asteroids just a few miles across. This diverse collection of worlds represents a miniature solar system in its own right, with Jupiter playing the role of a central star. The gravitational relationships within the Jovian system operate on scales that dwarf anything in the Earth-Moon system. Io, the innermost large moon, experiences tidal forces from Jupiter that are thousands of times stronger than the tidal forces Earth exerts on our moon. These forces generate so much heat within Io that the moon has become the most volcanically active world in our solar system, with over 400 active volcanoes dotting its surface. The volcanic activity on Io operates on scales that challenge our understanding of planetary geology. Some volcanic plumes shoot material over 300 miles high, reaching altitudes where spacecraft orbit around Earth. The total heat output from Io's volcanic activity exceeds the heat output of all terrestrial volcanoes, combined by a factor of 10 or more. This isn't just geological activity, it's geological hyperactivity driven by Jupiter's immense gravitational field. Europa, the second of Jupiter's large moons, harbours what may be the most significant ocean in our solar system. Beneath its icy surface lies a global ocean containing more than twice as much water as all of Earth's oceans combined. This hidden sea exists because Jupiter's tidal forces generate enough heat to keep the water liquid despite Europa being much farther from the Sun than Earth. The scale of Europa's subsurface ocean is staggering. Recent estimates suggest it may be 40 to 100 miles deep compared to Earth's oceans, which average less than 2.5 miles in depth. The total volume of this alien ocean dwarfs all terrestrial bodies of water, making Europa potentially the most water-rich world in our solar system. But Europa's ocean isn't just large, it's also potentially habitable. The interaction between the ocean and Europa's rocky interior may create hydrothermal vents similar to those found on Earth's ocean floors. These environments could provide the energy and chemical ingredients necessary for life to develop and thrive. The possibility that Jupiter's tidal heating could power an entire biosphere beneath Europa's ice represents one of the most exciting prospects in astrobiology. Ganymede, Jupiter's largest moon, is itself larger than the planet Mercury and possesses its own magnetic field generated by a liquid iron core. The interaction between Ganymede's magnetic field and Jupiter's creates complex electromagnetic phenomena that can be observed from Earth. Recent observations have detected auroras at Ganymede's poles, created by charged particles from Jupiter's magnetosphere interacting with Ganymede's thin atmosphere. The magnetic interaction between Jupiter and Ganymede also provides evidence for yet another subsurface ocean within Ganymede's interior. The way Ganymede's magnetic field responds to Jupiter's changing magnetic environment indicates the presence of a conducting layer, most likely a salty ocean sandwiched between layers of ice deep within the moon's interior. Callisto, the outermost of Jupiter's large moons, presents a different face of the Jovian system. Its heavily cratered surface records billions of years of impacts, providing a window into the early history of our solar system, when bombardment by asteroids and comets was much more intense. The preservation of these ancient scars tells us that Callisto has remained geologically inactive throughout most of its history, unlike its inner companions that have been reshaped by Jupiter's tidal forces. The diversity within Jupiter's moon system demonstrates how the planet's gravitational influence creates different environments at different distances. Close to Jupiter, tidal forces dominate, creating geologically active worlds like Io and Europa. Farther out, these forces weaken, allowing moons like Callisto to preserve ancient surface features. This gradient of gravitational influence creates a natural laboratory for studying how tidal forces affect planetary evolution. Beyond the 4 large Galilean satellites, Jupiter's gravitational reach extends to capture dozens of smaller moons. Many of these are likely asteroids that wandered too close to Jupiter and became permanently trapped in its gravitational field. Some of these captured moons have highly elliptical orbits that take them millions of miles from Jupiter before swinging back in close approaches. The scale of Jupiter's gravitational capture zone is enormous. Objects can be captured into orbit around Jupiter from distances comparable to the Earth-Moon separation. This capture process continues today, as Jupiter occasionally snares passing asteroids or comets, adding new members to its already extensive family of satellites. The study of Jupiter's moon system has also revealed the complex orbital dynamics that operate within the planet's gravitational field. The three innermost large moons are locked in a precise gravitational resonance, with Io completing 4 orbits for every 2 orbits of Europa and every 1 orbit of Ganymede. This mathematical precision isn't coincidental, but represents a stable configuration that has persisted for billions of years. These orbital resonances demonstrate how Jupiter's gravity creates order within apparent chaos. While the gravitational interactions within the Jovian system are incredibly complex, involving dozens of moons and countless smaller objects, they settle into stable patterns that can persist for geological ages. The same gravitational forces that create tidal heating and geological activity also maintain the precise orbital relationships that keep the system stable. Recent missions to Jupiter have revealed that the planet's influence on its moons extends beyond simple gravitational and tidal effects. Jupiter's powerful magnetosphere creates a radiation environment that continuously bombards the surfaces of its inner moons, driving chemical changes and creating exotic compounds that don't exist naturally on Earth. Over billions of years, this radiation processing has fundamentally altered the surface compositions of moons like Europa and Ganymede. The interaction between Jupiter's magnetosphere and its moons also creates electrical currents that flow through the vacuum of space. The current flowing between Jupiter and Io carries millions of amperes, more electrical power than many terrestrial power grids. This current flow heats Jupiter's upper atmosphere and contributes to the planet's powerful auroral displays. The auroras on Jupiter operate on scales that dwarf their terrestrial counterparts. Individual auroral features can be larger than Earth and persist for days or weeks. The total power output of Jupiter's auroras exceeds the power output of all human civilization by factors of thousands or millions. These aren't just pretty lights in the sky. They're manifestations of electromagnetic processes operating on planetary scales. The scale of electromagnetic phenomena around Jupiter extends far beyond the planet's physical boundaries. Radio emissions from Jupiter can be detected by amateur radio operators on Earth using relatively simple equipment. These radio signals are generated by electrons spiraling along Jupiter's magnetic field lines at nearly the speed of light, creating a natural radio transmitter more powerful than any human-built device. Jupiter's radio emissions vary in complex patterns that reflect the dynamic interactions between the planet's magnetosphere and its moons. When Io passes through certain regions of Jupiter's magnetic field, the radio output increases dramatically, creating what scientists call Io-controlled emissions. These radio storms can be detected from Earth despite the enormous distance, demonstrating the incredible scale of the electromagnetic processes operating within the Jovian system. The study of Jupiter's electromagnetic environment has provided insights into similar processes that may occur around other giant planets throughout the galaxy. As we discover more exoplanets, particularly gas giants similar to Jupiter, understanding the electromagnetic phenomena around our own giant planet becomes crucial for interpreting observations of distant worlds. Jupiter's massive scale continues to influence our understanding of planetary formation and evolution throughout the universe. The planet serves as a prototype for gas giants, providing detailed information about processes that probably occur around countless other stars. Every new discovery about Jupiter's structure, composition, or behavior adds to our understanding of how planetary systems form and evolve. The recent discovery that Jupiter's core is much larger and more diffuse than expected has implications for models of giant planet formation throughout the galaxy. If Jupiter's formation involved violent impacts and mixing processes, similar events probably occurred during the formation of gas giants around other stars. This means that the internal structures of exoplanets may be much more complex and varied than we previously assumed. The ongoing study of Jupiter's massive scale also provides insights into the fundamental physics of planetary interiors. The extreme pressures and temperatures within Jupiter create conditions that can't be replicated in terrestrial laboratories. By studying Jupiter's structure and behavior, scientists can test theories about the behavior of matter under extreme conditions, advancing our understanding of physics itself. As our exploration tools become more sophisticated, we continue to discover new aspects of Jupiter's enormous scale and influence. Future missions to Jupiter will undoubtedly reveal even more surprises about this giant world, adding new chapters to the story of how massive objects shape the cosmic environments around them. The question of how massive Jupiter truly is extends far beyond simple measurements of size and weight. Jupiter's mass creates gravitational fields, electromagnetic phenomena, and dynamic processes that operate on scales spanning millions of miles and billions of years. The planet's influence permeates every aspect of our solar system's structure and evolution, making Jupiter not just the largest planet but also the most influential member of our cosmic family. Understanding Jupiter's true scale requires us to step back and consider time itself. This massive world has been performing its gravitational symphony for over 4.5 billion years, and the cumulative effects of its influence have shaped every corner of our solar system in ways that continue to unfold today. When we talk about Jupiter's mass affecting other objects, we're not just talking about immediate gravitational pulls. We're talking about processes that operate across geological timescales, where tiny gravitational nudges accumulate over millions of orbital periods to create dramatic changes in the architecture of our solar system. Consider the asteroid belt, that collection of rocky debris orbiting between Mars and Jupiter. At first glance, it might seem like a random scattering of leftover material from the solar system's formation. But look more closely, and you'll see the invisible hand of Jupiter's gravity written across its structure. The belt contains distinct gaps, called Kirkwood gaps, where asteroids are notably absent. These aren't random empty spaces. They're the result of Jupiter's gravitational resonances clearing out specific orbital zones over millions of years. An asteroid unfortunate enough to orbit in one of these resonance zones experiences a gravitational tug from Jupiter at exactly the same point in its orbit, again and again, for millions of years. Each tug is tiny, almost imperceptible. But over time, these accumulated nudges increase the asteroid's orbital eccentricity until its path becomes so elongated that it either collides with another object or gets ejected from the belt entirely. The scale of this gravitational sculpting becomes apparent when you realize that Jupiter is performing this orbital engineering across distances of hundreds of millions of miles. The planet doesn't need to be anywhere near these asteroids to control their fate. Its massive gravity reaches across the void, subtly but inexorably reshaping the distribution of matter throughout the solar system. This same gravitational influence extends much farther out, affecting objects in the distant reaches of our solar system. The Kuiper Belt, that region beyond Neptune where Pluto and thousands of other icy bodies orbit, bears the signature of Jupiter's gravitational influence. Even at distances of 3 to 5 billion miles from Jupiter, objects in the Kuiper Belt move in patterns that reflect the giant planet's presence. Some of the most dramatic examples of Jupiter's long-range gravitational influence come from studying comets. These icy visitors from the outer solar system often owe their spectacular appearances to gravitational encounters with Jupiter that occurred decades or centuries earlier. Jupiter can capture a comet from a highly elongated orbit and shepherd it into a shorter period orbit that brings it back to the inner solar system every few years. The scale of these gravitational manipulations is staggering. Jupiter can take a comet that originally took thousands of years to complete one orbit and transform it into a regular visitor with an orbital period of just 5 or 6 years. Alternatively, Jupiter can accelerate a comet to such high velocities that it's ejected from the solar system entirely, sent on a one-way journey to interstellar space. The famous comet Shoemaker-Levy 9 Provide 1994. This comet had a dramatic demonstration of Jupiter's gravitational power indeed being captured by Jupiter's gravity during a previous close encounter, and the tidal forces from the giant planet tore it apart into a string of fragments. When these fragments eventually collided with Jupiter, they created impact sites larger than Earth and explosions visible from telescopes around our planet. But Jupiter's gravitational influence operates on scales even larger than individual comet encounters. The planet acts as a kind of gravitational traffic controller for the entire outer solar system, determining which objects from the distant Oort cloud eventually make their way inward to become visible comets. When these distant icy bodies are nudged by passing stars or galactic tides, their subsequent journeys through the solar system are largely controlled by Jupiter's massive gravity. The Oort cloud itself, that spherical shell of comets surrounding our solar system at distances of thousands of astronomical units, exists in its current form partly because of Jupiter's gravitational influence during the early stages of solar system formation. As Jupiter grew to its current size, its gravity helped scatter countless icy planetesimals outward, populating the distant reaches of our solar system with the reservoir of comets that occasionally visit the inner solar system today. This scattering process operated on truly cosmic scales. Objects that formed relatively close to the Sun, perhaps in the region where the giant planets now orbit, were flung outward by Jupiter's gravity to distances thousands of times farther from the Sun. Some of these scattered objects may have been ejected from the solar system entirely, contributing to the population of rogue planets that drift through interstellar space. The scale of Jupiter's influence becomes even more impressive when we consider its role in delivering water to the inner solar system. During the early bombardment period, roughly 4 billion years ago, Jupiter's gravity scattered water-rich asteroids and comets throughout the solar system. Some of these objects collided with Earth, potentially providing much of the water that fills our oceans today. Recent computer simulations suggest that without Jupiter's gravitational stirring, Earth might have remained a dry, lifeless world. The giant planet's influence was crucial in delivering the raw materials necessary for life to develop on our planet. In a very real sense, every drop of water in Earth's oceans may be there because of gravitational interactions with Jupiter that occurred billions of years ago. But Jupiter's role in shaping our solar system extends beyond just moving objects around. The planet's massive gravity has also influenced the very structure of space itself in our cosmic neighborhood. Einstein's theory of general relativity tells us that mass curves space-time, and Jupiter's enormous mass creates a significant gravitational well that affects the trajectories of everything passing nearby. This curvature of space-time around Jupiter is so pronounced that it affects the paths of spacecraft visiting the outer solar system. Mission planners routinely use Jupiter's gravity to accelerate and redirect spacecraft, a technique called a gravitational slingshot or gravity assist. By carefully timing a spacecraft's approach to Jupiter, engineers can increase its velocity and change its direction without using any additional fuel. The Voyager missions provide perhaps the most famous example of using Jupiter's gravity for space exploration. Both Voyager 1 and Voyager 2 used Jupiter's immense gravitational field to accelerate toward the outer planets, achieving velocities that would have been impossible with chemical rockets alone. The gravitational boost from Jupiter allowed these spacecraft to visit Saturn, Uranus, and Neptune, and eventually become the first human-made objects to enter interstellar space. The precision required for these gravitational assists demonstrates the predictable nature of Jupiter's massive gravitational field. Engineers can calculate exactly how Jupiter's gravity will affect a spacecraft's trajectory years in advance, planning complex multi-planet missions that rely on precise timing and positioning. The fact that these calculations work so perfectly is a testament to our understanding of how Jupiter's mass curves space-time. But Jupiter's gravitational influence isn't limited to objects passing through the solar system. The planet's massive presence actually affects the Sun itself, causing our star to wobble slightly as Jupiter orbits around it. This wobble is tiny from our perspective, but it's measurable and has been detected from Earth. The Sun-Jupiter system actually orbits around their common center of mass, called the barycenter. Because Jupiter is so much less massive than the Sun, this barycenter lies just outside the Sun's surface. As Jupiter completes its 12-year orbit, it pulls the Sun around this barycenter, creating a regular wobbling motion that can be detected by sensitive instruments. This solar wobble caused by Jupiter has become one of the primary techniques for discovering planets around other stars. When astronomers observe a distant star wobbling in a regular pattern, they know there's likely a massive planet, probably similar to Jupiter, orbiting that star. Hundreds of exoplanets have been discovered using this technique, many of them gas giants comparable in mass to Jupiter. The detection of these Jupiter-like exoplanets has revealed something surprising about our solar system. Most of the gas giants discovered around other stars orbit much closer to their host stars than Jupiter orbits the Sun. These hot Jupiters complete their orbits in days or weeks rather than Jupiter's 12-year period. This suggests that our solar system may be somewhat unusual in having its giant planet in a distant orbit. The prevalence of hot Jupiters around other stars has led to new theories about planetary migration during solar system formation. It appears that gas giants commonly migrate inward toward their host stars after forming in the outer regions of planetary systems. Jupiter's location in our solar system suggests that something stopped its inward migration, allowing it to remain in its current distant orbit. The most likely explanation involves Saturn, the second largest planet in our solar system. Computer simulations suggest that as both Jupiter and Saturn grew and began migrating inward, their gravitational interaction created a resonance that reversed their motion, sending both planets back outward to roughly their current positions. This gravitational dance between the two gas giants may have been the crucial event that prevented Jupiter from becoming a hot Jupiter and destroying the inner solar system. The scale of this early planetary migration is difficult to comprehend. Jupiter, with a mass greater than all other planets combined, may have traveled hundreds of millions of miles inward toward the Sun before reversing course and moving back out to its current position. The gravitational chaos this journey must have created throughout the early solar system would have affected every object in the solar nebula. This migration scenario helps explain many puzzling features of our solar system's architecture. Mars's small size compared to Earth and Venus may result from Jupiter's inward journey truncating the planet's formation. The asteroid belt's current structure may reflect the gravitational stirring that occurred as Jupiter passed through the region. Even the characteristics of Earth's orbit may have been influenced by Jupiter's early migration. The timing of Jupiter's formation and migration may have been crucial for the development of life on Earth. If Jupiter had formed earlier or later, or if its interaction with Saturn had played out differently, the inner solar system might look completely different today. Earth might never have formed in the habitable zone, or it might have been scattered into a different orbit where liquid water couldn't exist. These possibilities highlight how Jupiter's massive scale has influenced not just the physical structure of our solar system, but also the conditions that allowed life to develop on Earth. The giant planet's gravitational influence has been shaping our cosmic environment for over 4 billion years, creating the stable, protective solar system architecture that makes Earth's biosphere possible. Recent discoveries about exoplanetary systems have given us new perspectives on Jupiter's role in our solar system. Many of the planetary systems discovered around other stars look very different from our own, with giant planets in close orbits and smaller planets scattered throughout their systems. The apparent rarity of solar systems with Jupiter-like planets in Jupiter-like orbits suggests that our cosmic neighborhood may be more special than we previously realized. The study of these exoplanetary systems has also revealed that the formation of gas giants like Jupiter may be more complex and varied than we once thought. Different stellar environments, different amounts of available material, and different timing of formation events can lead to gas giants with very different characteristics and orbital properties. Jupiter's role as a template for understanding gas giants throughout the galaxy makes every new discovery about our local giant planet significant for astronomy as a whole. The internal structure revealed by the Juno mission, the complex atmospheric dynamics observed by ground-based telescopes, and the electromagnetic phenomena detected by spacecraft all provide insights into processes that probably occur around gas giants throughout the universe. The scale of Jupiter's influence on our understanding of planetary science extends far beyond our solar system. As we prepare for future missions that will search for life around other stars, Jupiter serves as a crucial example of how gas giants can both protect and threaten the development of life on smaller, rocky planets. Understanding Jupiter's role in our solar system helps us predict where we might find habitable worlds around other stars. But perhaps the most profound aspect of Jupiter's massive scale is how it demonstrates the interconnectedness of everything in our solar system. This giant planet doesn't exist in isolation. Its gravity reaches across billions of miles to influence objects throughout our cosmic neighborhood. Its magnetic field extends far beyond its physical boundaries to interact with the solar wind and create phenomena visible from Earth. Its atmospheric dynamics generate radio emissions that can be detected by amateur astronomers with backyard equipment. Jupiter's story is really the story of our entire solar system. The giant planet's formation, evolution, and ongoing influence have shaped every aspect of our cosmic environment, from the water in Earth's oceans to the structure of the asteroid belt, from the orbits of comets to the characteristics of the outer planets. Jupiter's massive presence has left its mark on virtually everything in our solar neighborhood. As we continue to explore Jupiter with increasingly sophisticated instruments and techniques, we're not just learning about one planet, we're uncovering the fundamental processes that govern planetary formation and evolution throughout the universe. Jupiter's massive scale provides a window into the cosmic forces that shape planetary systems everywhere, making this giant world one of the most important objects in our quest to understand our place in the cosmos. The question of Jupiter's true scale ultimately leads us to a deeper appreciation of the delicate balance that allows our solar system to exist as it does today. This massive world, with its complex internal structure, powerful magnetic field, and extensive family of moons, represents one of nature's most impressive achievements. Yet it also reminds us how much we still have to learn about the cosmic processes that created our solar system and continue to shape its evolution. Every new measurement of Jupiter's gravitational field, every fresh observation of its atmospheric dynamics, and every discovery about its internal structure adds another piece to the puzzle of how massive objects influence their cosmic environments. Jupiter's scale encompasses not just physical dimensions, but also gravitational reach, electromagnetic influence, and evolutionary impact that extends across billions of years and billions of miles. In contemplating Jupiter's massive scale, we're really contemplating the fundamental question of how matter organizes itself in the universe. From the quantum interactions that govern atomic behavior to the gravitational forces that shape galactic structure, Jupiter represents a remarkable example of how mass and energy can combine to create complex, dynamic systems that influence everything around them. The giant planet's story is still being written. As Jupiter continues its stately orbit around the Sun, its gravitational influence continues to shape the evolution of our solar system. New moons may be captured, asteroid orbits may be altered, and comets may be redirected onto new paths. The massive scale that has defined Jupiter's role in our solar system for over 4 billion years will continue to influence our cosmic neighborhood for billions of years to come. Understanding Jupiter's true scale requires us to think beyond simple measurements and consider the planet's role in the grand symphony of gravitational, electromagnetic, and thermodynamic processes that govern our solar system. In its massive presence, we see reflected the fundamental forces that shape all cosmic structures, from planetary systems to galaxies themselves. Jupiter's scale is ultimately a window into the scale of the universe itself, reminding us that we inhabit a cosmos where massive objects routinely influence their environments across distances and timescales that challenge human comprehension. As we peer deeper into Jupiter's colossal realm, we encounter phenomena that challenge our very understanding of what it means to be a planetary body. The boundaries between planet and star begin to blur when we examine the incredible pressures and temperatures that exist within Jupiter's core region. Deep within Jupiter's interior, roughly 20,000 miles below the cloud tops we can observe, conditions become so extreme that the very nature of matter itself transforms. The pressure at this depth exceeds 40 million times Earth's atmospheric pressure. To put this in perspective, if you could somehow transport a piece of granite from Earth's surface to this depth within Jupiter, it would be compressed to a density greater than gold. At these crushing pressures, hydrogen undergoes a transformation that exists nowhere else in our solar system. The familiar gas that fills party balloons on Earth becomes a metallic liquid that conducts electricity like copper wire. This isn't just a simple phase change like ice melting into water. This is matter being forced into a state that we can barely recreate in our most advanced laboratories, and then only for microseconds. The sheer volume of this metallic hydrogen ocean within Jupiter staggers the imagination. We're talking about a sphere of liquid metal larger than Earth itself, spinning rapidly as Jupiter rotates every 10 hours. This creates the largest dynamo in our solar system, generating electrical currents that would power human civilization for billions upon billions of years. But the electromagnetic phenomena surrounding Jupiter extend far beyond just its magnetic field strength. The planet essentially creates its own version of the aurora borealis, but on a scale that dwarfs anything we see on Earth. Jupiter's auroras cover areas larger than our entire planet and shine with an intensity that would be visible from space even during Jupiter's daytime hours. These auroral displays aren't just pretty light shows. They represent the visible manifestation of electrical processes operating on planetary scales. The total energy involved in Jupiter's auroral activity exceeds the combined power output of every power plant that has ever existed on Earth. We're witnessing electromagnetic forces so powerful that they reshape the very structure of space around Jupiter. The interaction between Jupiter's magnetosphere and the solar wind creates a bow shock wave that begins forming millions of miles before the solar wind even encounters Jupiter's magnetic field. It's as if Jupiter creates its own weather system in the vacuum of space, deflecting and reshaping the stream of charged particles flowing outward from our Sun. This electromagnetic dominance extends throughout Jupiter's entire moon system. The electrical current flowing between Jupiter and its moon Io carries enough power to supply the energy needs of a major metropolitan area. This current flow creates a glowing plasma torus that encircles Jupiter at Io's orbital distance, forming an invisible ring of superheated gas that's larger than the orbit of our own moon. But perhaps the most mind-bending aspect of Jupiter's scale becomes apparent when we consider its role in cosmic time. This massive world has been performing its gravitational symphony for over 4.5 billion years. Every asteroid deflected, every comet redirected, every subtle orbital adjustment accumulated over geological ages represents Jupiter exercising its massive influence across timescales that dwarf human comprehension. During Earth's early bombardment period, when our planet was still cooling from its formation, Jupiter was already acting as a cosmic traffic controller. The water in our oceans, the carbon in our bodies, the iron in our blood, all may have reached Earth because of gravitational interactions with Jupiter that occurred when our planet was still molten. The scale of Jupiter's protective influence becomes evident when we examine Earth's impact history. Computer models suggest that without Jupiter's gravitational presence, our planet would experience catastrophic asteroid and comet impacts at rates hundreds of times higher than we actually observe. The extinction event that killed the dinosaurs might have been routine rather than exceptional. Yet Jupiter's gravitational influence operates with a subtlety that's almost artistic in its precision. The planet doesn't simply deflect dangerous objects away from Earth like some cosmic baseball bat. Instead, it conducts a complex gravitational ballet that has been choreographing the movement of objects throughout our solar system for billions of years. Consider the Trojan asteroids, those rocky bodies that share Jupiter's orbit around the Sun, but remain fixed in stable gravitational zones 60 degrees ahead of and behind the giant planet. These aren't recent captures. These asteroids have been locked in this precise gravitational dance with Jupiter for potentially the entire history of our solar system. We're looking at gravitational relationships that have remained stable across geological ages. The mathematical precision required to maintain these orbital relationships demonstrates Jupiter's role as more than just a massive object. The planet acts as a gravitational anchor point that helps organize and stabilize the architecture of our entire solar system. Without Jupiter's massive presence, the neat arrangement of planetary orbits we observe today might never have developed. Recent discoveries have revealed that Jupiter's gravitational influence extends even further than we previously imagined. The planet's gravity helps determine the orbital characteristics of objects in the distant Kuiper Belt, that region beyond Neptune, where Pluto and thousands of other icy bodies reside. Even at distances of billions of miles, Jupiter's gravitational signature can be detected in the orbital patterns of these remote worlds. The discovery of the Kuiper Belt objects has provided new insights into Jupiter's role during the early formation of our solar system. Many of these distant objects bear the gravitational fingerprints of encounters with Jupiter that occurred billions of years ago. Some were scattered outward by Jupiter's gravity during early migration phase, while others were captured into complex their current orbits through gravitational interactions. But Jupiter's influence on the Kuiper Belt reveals something even more profound about the planet's massive scale. We're seeing evidence of gravitational processes that operated across the entire solar system during its formation. Jupiter didn't just clear out its immediate neighborhood. Its gravitational reach extended to the very edges of our solar system, helping to shape the distribution of matter across distances measured in billions of miles. The study of Jupiter's gravitational influence has also provided insights into the formation of other planetary systems throughout our galaxy. As we discover more exoplanets around distant stars, we're finding that systems with Jupiter-like planets in Jupiter-like orbits appear to be relatively rare. This suggests that our solar system's architecture, with its giant planet in a distant, stable orbit, may represent a special configuration that's not easily achieved. The rarity of solar systems like ours has profound implications for the search for life beyond Earth. Jupiter's role in protecting the inner solar system from impact while allowing stable planetary orbits to develop may be a crucial factor in enabling the long-term stability necessary for life to evolve. We may owe our very existence to the precise timing and positioning of Jupiter's formation billions of years ago. The electromagnetic environment around Jupiter continues to reveal new surprises as our observational techniques become more sophisticated. Recent radio observations have detected emissions from Jupiter that vary in complex patterns, reflecting the dynamic interactions between the planet's magnetosphere and its moons. These radio signals are so powerful that they can be detected by amateur astronomers using relatively simple equipment. Despite traveling across hundreds of millions of miles of space, the radio emissions from Jupiter operate like a natural broadcasting station, transmitting signals that carry information about conditions deep within the planet's magnetosphere. By studying these emissions, scientists can probe regions of space around Jupiter that no spacecraft has ever visited, revealing details about magnetic field structures and particle populations that would be impossible to measure directly. But perhaps the most remarkable aspect of Jupiter's radio emissions is their sheer power. The Jupiter exceeds the total radio output from output of our Sun at certain frequencies. We're dealing with electromagnetic processes so energetic that they rival the activity of our local star. Yet they're generated by a planet that produces no nuclear fusion. The source of this incredible electromagnetic activity lies in the complex interactions between Jupiter's rapid rotation, its powerful magnetic field, and the constant stream of charged particles flowing outward from the Sun. As Jupiter spins every 10 hours, it drags its magnetic field through the solar wind, creating electrical currents and accelerating particles to incredible velocities. These accelerated particles create synchrotron radiation as they spiral along Jupiter's magnetic field lines at nearly the speed of light. The result is a natural particle accelerator more powerful than anything humans have ever built, operating continuously for billions of years and generating radio emissions detectable across interplanetary distances. The scale of electromagnetic phenomena around Jupiter extends beyond just radio waves. The planet generates emissions across the entire electromagnetic spectrum, from low-frequency radio waves to high-energy X-rays. Each wavelength reveals different aspects of the complex processes operating within Jupiter's magnetosphere, painting a picture of electromagnetic activity that operates on scales spanning millions of miles. Jupiter's X-ray emissions, first detected by space-based telescopes, reveal auroral processes occurring in the planet's upper atmosphere. These X-rays are generated when high-energy particles from Jupiter's magnetosphere collide with atoms in the planet's thin upper atmosphere, creating emissions that pulse in rhythm with Jupiter's 10-hour rotation period. The discovery of Jupiter's X-ray auroras has provided new insights into the planet's atmospheric composition and the nature of its upper atmosphere. The emissions reveal the presence of oxygen and other heavy elements in Jupiter's atmosphere, materials that were incorporated during the planet's formation from the primordial solar nebula. But the electromagnetic phenomena around Jupiter also create challenges for spacecraft exploration. The radiation environment near Jupiter is so intense that it poses serious risks to electronic equipment. Spacecraft visiting Jupiter must be specially designed with radiation-hardened electronics and carefully planned trajectories that minimize exposure to the most dangerous regions of the magnetosphere. The Juno spacecraft, currently orbiting Jupiter, represents a triumph of engineering in designing systems that can survive the harsh radiation environment around the giant planet. The spacecraft follows a highly elliptical orbit that carries it close to Jupiter for detailed observations, but then takes it far from the planet to minimize radiation exposure. Even with these precautions, the mission has a limited lifetime due to the cumulative effects of radiation damage. The challenges of exploring Jupiter's radiation environment highlight the extreme nature of the electromagnetic processes operating around the giant planet. We're dealing with radiation levels that would be instantly lethal to any unprotected life form. Yet these same processes may play important roles in driving chemical reactions and energy flows throughout the Jovian system. The interaction between Jupiter's powerful magnetosphere and its moons creates unique chemical environments that don't exist anywhere else in our solar system. The constant bombardment of charged particles drives chemical reactions on the surfaces of moons like Europa and Ganymede. Recent studies have suggested that the radiation environment around Jupiter might actually enhance the habitability of its moons rather than destroying it. The energy from charged particle bombardment could drive chemical reactions in subsurface oceans, providing energy sources for potential ecosystems that don't depend on sunlight. This possibility transforms our understanding of Jupiter's massive scale from simply a story of size and gravity to a story of how extreme environments can create unexpected opportunities for complex chemistry and potentially even life. The giant planet's electromagnetic influence may extend to fostering the very conditions necessary for biology to develop in its alien ocean worlds. The study of Jupiter's moons has revealed that the planet's massive scale creates not just one environment, but a diverse collection of worlds, each shaped by different aspects of Jupiter's influence. Close to the planet, tidal forces dominate, creating geologically active worlds like Io with its sulfur volcanoes and Europa with its subsurface ocean. Farther out, electromagnetic effects become more important, while gravitational capture processes create families of small, irregular moons. This diversity within the Jovian system demonstrates how a single massive object can create multiple distinct environments through different physical processes. Jupiter acts like a planetary system in miniature, with different zones characterized by different dominant forces and different evolutionary pathways. The ongoing exploration of Jupiter's moon system continues to reveal new complexities and surprises. Recent observations have detected water vapor plumes erupting from Europa's surface, providing direct evidence of the subsurface ocean and offering potential targets for future missions seeking signs of life. Similar plumes have been detected from other icy moons, suggesting that subsurface oceans may be common throughout the outer solar system. These discoveries highlight how Jupiter's massive gravitational influence extends beyond simple orbital mechanics to create and maintain environments that could potentially harbor life. The tidal heating generated by Jupiter's gravity may be one of the most important energy sources for biology in the outer solar system, powering ecosystems that could exist for billions of years in the darkness far from the sun. The scale of potential habitability within the Jovian system staggers the imagination. If life exists in the subsurface oceans of Europa, Ganymede, and other Jovian moons, the total volume of potentially habitable space within Jupiter's influence could exceed the habitable volume of Earth's biosphere. We may be looking at a region of space where biology operates on scales comparable to entire terrestrial ecosystems. But the story of Jupiter's massive scale continues to evolve as our understanding deepens and our observational capabilities improve. Each new mission to Jupiter reveals phenomena that weren't predicted by our models, forcing us to expand our concepts of what's possible in planetary science. The James Webb Space Telescope has recently provided unprecedented views of Jupiter's atmospheric dynamics, revealing temperature and chemical variations that operate on scales spanning thousands of miles. These observations are showing us that Jupiter's atmosphere is even more complex and dynamic than we realized, with chemical processes and energy flows that continue to surprise researchers. Future missions to Jupiter will undoubtedly reveal even more aspects of the planet's incredible scale and influence. Proposed missions include orbiters that will study Jupiter's interior structure in even greater detail, landers that will probe the atmospheres of its moons, and perhaps even submarines that will explore the subsurface oceans beneath the ice. Each of these future discoveries will add new chapters to the story of Jupiter's massive scale, revealing new ways that this giant planet influences its environment and shapes the evolution of our solar system. The question of how massive Jupiter truly is continues to expand beyond simple measurements to encompass the planet's role in cosmic processes that operate across vast scales of space and time. As we contemplate Jupiter's massive presence in our solar system, we're really contemplating the fundamental forces that govern the universe itself. Gravity, electromagnetism, and thermodynamics all come together in Jupiter to create phenomena that operate on scales from the subatomic to the planetary. The giant planet serves as a natural laboratory where we can study processes that occur throughout the cosmos. Jupiter's massive scale ultimately reminds us that we live in a universe where matter and energy organize themselves into structures of breathtaking complexity and beauty. From the quantum interactions that govern the behavior of metallic hydrogen in Jupiter's core to the gravitational forces that shepherd comets across billions of miles, Jupiter embodies the remarkable ability of physical processes to create order and complexity from apparent chaos. The giant planet story is far from over. As Jupiter continues its stately journey around the Sun, its massive influence will continue to shape our solar system for billions of years to come. New gravitational encounters will redirect comets and asteroids. Tidal forces will continue to heat its moons, and electromagnetic processes will persist in accelerating particles and generating radio emissions detectable across interplanetary space. Understanding Jupiter's true massive scale requires us to appreciate not just what the planet is today, but what it has been throughout the history of our solar system, and what it will continue to be as our cosmic neighborhood evolves. In Jupiter's massive presence, we see reflected the ongoing creative processes that continue to shape our universe on scales that challenge human comprehension, but inspire endless wonder and discovery. The more we contemplate Jupiter's staggering dimensions, the more we begin to understand that we're not simply looking at a large planet. We're witnessing what might be considered a cosmic accident that fundamentally changed the character of our entire solar system. Jupiter represents the threshold between what we call a planet and what astronomers classify as a brown dwarf, those mysterious objects that that hover in the twilight zone between planets and stars. If Jupiter had managed to accumulate just a bit more mass during its formation, perhaps 50 to 80 times more material, nuclear fusion would have ignited in its core. Instead of gazing up at a single sun in our sky, we might be living in a binary star system with two sources of light and heat. Earth's climate would be radically different, shaped by the complex interplay of radiation from two stellar objects. Our seasons, our weather patterns, our very evolution as a species might have followed completely different pathways. This tantalizing what-if scenario highlights just how close Jupiter came to transforming our solar system into something utterly alien. The difference between our current reality and a completely different cosmic arrangement came down to gravitational dynamics and material availability during those crucial first few million years of solar system formation. Jupiter consumed most of the available material in its region of space, but not quite enough to cross that magical threshold into stellar ignition. The implications of Jupiter's near-stellar mass become even more profound when we consider the delicate balance that allowed terrestrial planets like Earth to form at all. During the chaotic early period of solar system evolution, Jupiter's gravitational influence could have easily disrupted the formation of rocky worlds in the inner solar system. The fact that we exist at all may depend on the precise timing of Jupiter's growth and the specific gravitational dance it performed with its neighboring worlds. Recent computer simulations of early solar system dynamics reveal scenarios that are almost too dramatic to believe. Picture Jupiter as a massive gravity-wrecking ball, Ational W migrating inward toward the young sun during the first few million years after its formation. As this giant world moved through the inner solar system, it would have scattered planetesimals, disrupted forming worlds, and potentially prevented the accumulation of material that eventually became the terrestrial planets. But something remarkable happened that saved our solar system from this gravitational catastrophe. As Saturn grew to significant size and began its own migration, gas, the two giants became locked in a gravitational resonance that reversed their inward journey. This cosmic ballet between Jupiter and Saturn, playing out over millions of years, sent both planets back toward the outer solar system, clearing the way for Earth, Venus, and Mars to complete their formation. This dance of the giants reveals Jupiter's role not just as our solar system's largest planet, but as an active architect of cosmic structure. The planet's massive presence didn't simply influence objects that happened to wander into its gravitational field. Instead, Jupiter's growth and migration actively shaped the distribution of material throughout our entire cosmic neighborhood, determining which worlds could form and where they could exist. The gravitational relationship between Jupiter and Saturn continues to influence our solar system today, billions of years after their initial migration. The two planets remain locked in a complex orbital resonance that affects the stability of their orbits and influences the behavior of smaller objects throughout the outer solar system. This ongoing gravitational partnership demonstrates how massive objects can maintain cooperative relationships across vast distances and enormous timescales. But Jupiter's architectural influence extends beyond just organizing the major planets. The giant world has spent billions of years fine-tuning the orbits of countless smaller objects, creating the complex structure we observe in asteroid families, comet populations, and the intricate dynamics of planetary ringward gap in systems. Every Kirk the asteroid belt, every captured comet in a short period orbit, every gravitational resonance that maintains orbital stability represents Jupiter exercising its massive influence with mathematical precision. The cumulative effect of these countless small gravitational interactions has been to create a solar system that operates like a vast clockwork mechanism. Objects move in predictable patterns. Orbital relationships remain stable across geological ages, and the overall architecture maintains itself through the complex interplay of gravitational forces. Jupiter serves as the primary gear in this cosmic clockwork, its massive presence providing the gravitational framework that keeps everything else in proper alignment. The planet's rapid rotation creates atmospheric dynamics that operate on scales and timescales that challenge our understanding of fluid mechanics. Wind systems that persist for centuries, storm cells larger than Earth, and chemical processes that transform simple molecules into complex organic compounds all play out across Jupiter's vast atmospheric canvas. The Great Red Spot, that iconic storm that has fascinated observers for over 3 centuries, represents just one example of the extraordinary scales on which Jovian weather operates. This single atmospheric feature contains more energy than all of Earth's weather systems combined, yet it maintains its structure and coherence across timescales that span human history. Recent observations have shown that the storm extends deep into Jupiter's atmosphere, reaching pressures and temperatures that would vaporize most terrestrial materials. But the Great Red Spot is shrinking, a reminder that even on Jupiter, change occurs across scales we can observe and measure. When systematic observations began in the late 19th century, this storm system was more than twice its current size. The fact that we're witnessing the evolution of this ancient tempest provides a unique window into atmospheric processes that operate on planetary scales. The shrinkage of the Great Red Spot raises fascinating questions about the long-term stability of Jupiter's atmospheric features. If this storm system, which has persisted for centuries, can change dramatically over human timescales, what does this tell us about the dynamic nature of Jupiter's entire atmospheric system? Are we observing a temporary fluctuation, or are we witnessing the gradual evolution of Jupiter's atmospheric structure? The chemical complexity of Jupiter's atmosphere adds another dimension to our understanding of the planet's massive scale. While the bulk composition remains relatively simple, dominated by hydrogen and helium, the trace compounds create a rich tapestry of chemical processes that operate across the planet's entire atmospheric volume. Organic molecules form and dissipate in chemical cycles that dwarf any terrestrial equivalent, processing quantities of material that exceed entire planetary masses. The colors we observe in Jupiter's clouds tell stories of chemistry operating on cosmic scales. The browns, reds, and yellows that give Jupiter its distinctive appearance result from complex organic compounds created through the interaction of lightning, radiation, and trace atmospheric gases. These chemical reactions occur throughout Jupiter's vast atmosphere, creating organic molecules in quantities that would fill Earth's oceans many times over. Lightning on Jupiter operates with intensities that make terrestrial thunderstorms seem gentle by comparison. Individual lightning bolts can be thousands of times more powerful than their Earth counterparts, generating radio emissions so intense they can be detected by spacecraft throughout the outer solar system. The energy released by Jovian lightning creates and destroys chemical compounds in processes that operate like a planetary-scale chemistry laboratory. The scale of chemical processing in Jupiter's atmosphere has implications that extend far beyond the planet itself. The organic compounds created in Jupiter's atmosphere may provide insights into the chemical processes that occurred during the early formation of our solar system, when similar conditions existed throughout the solar nebula. Jupiter may preserve chemical signatures from the dawn of our cosmic neighborhood, offering clues about the materials and processes that gave rise to all the planets. But Jupiter's chemical complexity extends beyond its atmosphere to include interactions with its extensive moon system. The giant planet's powerful magnetosphere drives chemical reactions on the surfaces of its moons, creating compounds that don't exist naturally elsewhere in our solar system. The bombardment of charged particles strips away surface materials and drives chemistry in subsurface environments, potentially creating the building blocks necessary for biology. The possibility that Jupiter's massive influence could foster rather than destroy the conditions for life represents one of the most intriguing aspects of the planet's role in our solar system. The tidal heating generated by Jupiter's gravity creates liquid water environments beneath the icy surfaces of multiple moons, while the planet's magnetosphere provides energy sources that could drive complex chemistry in these hidden oceans. Europa's subsurface ocean, maintained in liquid form by Jupiter's tidal forces, may contain more than twice as much water as all of Earth's oceans combined. This hidden sea has remained liquid for billions of years, protected beneath kilometers of ice and heated by the constant flexing of Europa's interior as Jupiter's gravity pulls and stretches the moon's rocky core. The longevity of Europa's ocean demonstrates Jupiter's ability to create and maintain habitable environments across geological timescales. While Earth's surface conditions have changed dramatically throughout our planet's history, Europa's subsurface ocean has likely remained stable for most of the history of our solar system. This stability, combined with the chemical energy provided by Jupiter's radiation environment, creates conditions that could potentially support ecosystems that have been evolving for billions of years. Recent detections of water vapor plumes erupting from Europa's surface provide direct evidence of the subsurface ocean and offer tantalizing possibilities for future exploration. These plumes carry material from Europa's hidden depths directly into space, where spacecraft can sample it without needing to drill through kilometers of ice. The chemical composition of these plumes could reveal whether Europa's ocean contains the organic compounds and energy sources necessary for life. Similar subsurface oceans likely exist within several of Jupiter's other moons, creating a collection of potentially habitable worlds within a single planetary system. Ganymede, Callisto, and possibly other Jovian satellites may harbour liquid water environments beneath their frozen surfaces, each one shaped by slightly different combinations of tidal heating, radioactive decay, and chemical composition. The scale of potential habitability within the Jovian system challenges our traditional concepts of where life might exist in the universe. Instead of looking only at planets orbiting within the narrow habitable zones around their stars, we must consider the possibility that gas giants like Jupiter create their own habitable zones through gravitational and electromagnetic processes. These zones could persist for billions of years, providing stable environments for biological evolution, even in regions of space that receive little energy from their host stars. The electromagnetic environment around Jupiter adds yet another layer of complexity to our understanding of the planet's massive influence. The radio emissions generated by Jupiter's magnetosphere carry enough power to supply major cities, yet they operate continuously across timescales measured in billions of years. This electromagnetic activity creates auroral displays that cover areas larger than Earth and generate emissions across the entire electromagnetic spectrum. The interaction between Jupiter's magnetic field and the solar wind creates phenomena that extend the planet's influence far beyond its physical boundaries. The bow shock formed where Jupiter's magnetosphere encounters the solar wind begins millions of miles from the planet, creating disturbances in the solar wind that can affect conditions throughout the outer solar system. These electromagnetic phenomena demonstrate how Jupiter's massive scale encompasses not just physical size, but also fields and forces that operate across vast regions of space. The planet's magnetic field lines stretch from Jupiter to beyond the orbit of Saturn, creating the largest single structure in our solar system after the Sun itself. Within this enormous magnetic environment, charged particles are accelerated to incredible energies, and complex electromagnetic processes operate on scales that dwarf any terrestrial equivalent. The study of Jupiter's magnetosphere has provided insights into similar phenomena that may occur around gas giant exoplanets throughout our galaxy. As we discover more Jupiter-like worlds orbiting other stars, understanding the electromagnetic environment around our own gas giant becomes crucial for interpreting observations of these distant systems. Jupiter serves as a prototype for gas giant magnetospheres, helping us understand how these massive worlds interact with their stellar environments. But perhaps the most profound aspect of Jupiter's massive scale lies in its role as a time machine, preserving conditions and processes from the early solar system within its deep interior. The planet's core region may contain materials that have remained largely unchanged since Jupiter's formation over 4 billion years ago. These primordial materials could provide direct insights into the conditions that existed during the birth of our solar system. The recent discovery that Jupiter's core is much larger and more diffuse than expected suggests that the planet's formation involved violent processes that mixed materials throughout its interior. Heavy elements that should have settled into a compact core appear to be distributed across a much larger region, possibly the result of massive impacts during Jupiter's early growth phase. These impacts may have involved objects as large as Earth, creating collisions so energetic that they fundamentally altered Jupiter's internal structure. The energy released by such impacts would have melted and vaporized enormous quantities of material, creating a partially molten interior that took millions of years to settle into its current configuration. The scale of these ancient impacts challenges our understanding of planetary formation processes. We're not talking about minor collisions between small objects, but about Earth-sized worlds smashing into a rapidly growing Jupiter at velocities measured in tens of kilometers per second. The energy released by each impact would have exceeded the total energy output of our Sun for extended periods, creating conditions more extreme than anything that exists in our solar system today. Yet somehow, Jupiter survived these cataclysmic events and continued growing, eventually reaching its current enormous size. The planet's ability to withstand such violent impacts and continue accumulating material demonstrates the remarkable resilience of gravitational systems and the extraordinary scales on which planetary formation operates. As we continue to explore Jupiter's massive scale through increasingly sophisticated observations and theoretical models, we're uncovering a story that encompasses the entire history of our solar system. From its chaotic birth in the primordial solar nebula, to its ongoing role as gravitational architect and electromagnetic powerhouse, Jupiter embodies processes that operate on the largest scales of space and time. The giant planet's influence extends from the quantum mechanical processes that govern the behavior of metallic hydrogen in its core to the galactic scale forces that occasionally nudge comets from the distant Oort cloud onto collision courses with the inner solar system. In Jupiter's massive presence, we see reflected the fundamental interconnectedness of all cosmic processes, from the smallest scales of matter to the largest structures in the universe. Jupiter's massive scale ultimately forces us to reconsider our most basic assumptions about what planets can be and do in our universe. When we look at this giant world through our most powerful telescopes, we're not just observing a large object floating in space. We're witnessing the ongoing operation of processes so vast and complex that they challenge the very limits of human comprehension. Consider for a moment the sheer temporal scale of Jupiter's influence. This massive world has been conducting its gravitational symphony for longer than complex life has existed on Earth. When the first simple cells were struggling to survive in our planet's primordial oceans, Jupiter was already a mature giant, shepherding comets and asteroids with the same gravitational precision we observe today. The ancient impacts that scarred our moon, the asteroid that may have triggered the extinction of the dinosaurs, the countless smaller collisions that have shaped Earth's geological history, all of these events occurred under Jupiter's watchful gravitational presence. The giant planet has been our cosmic guardian for so long that its protective influence has become woven into the very fabric of our planet's evolutionary story. This ongoing gravitational choreography operates with a subtlety that borders on the artistic. Jupiter doesn't simply act as a cosmic sledgehammer, smashing dangerous objects out of our way. Instead, the planet conducts a delicate dance of orbital adjustments, resonance captures, and long-term stability maintenance that has been fine-tuning our solar system's architecture for billions of years. The mathematical precision required for this gravitational artistry becomes apparent when we examine the orbital relationships that Jupiter has helped create and maintain. The spacing of planetary orbits, the structure of asteroid families, the periods of periodic comets, all of these follow patterns that reflect Jupiter's massive gravitational influence operating across vast scales of space and time. But perhaps the most remarkable aspect of Jupiter's scale emerges when we consider its relationship with time itself. This massive world operates on timescales that stretch from microseconds to billions of years. In its rapidly rotating interior, electrical currents change direction millions of times per second, generating the complex magnetic field patterns we observe. Yet the overall structure of that magnetic field has remained stable for geological ages, providing a consistent framework for electromagnetic processes throughout the Jovian system. The storms raging in Jupiter's atmosphere demonstrate this same temporal complexity. Individual lightning bolts last for milliseconds, yet the storm systems they help power can persist for centuries. The Great Red Spot has been continuously observed for over 300 years, making it older than any human institution on Earth. Yet it remains a dynamic, evolving system that continues to surprise researchers with its changing characteristics. This interplay between rapid change and long-term stability reflects something fundamental about the nature of complex systems operating on massive scales. Jupiter's atmosphere, magnetosphere, and gravitational field all exhibit this same pattern of short-term variability within long-term stability, creating a dynamic equilibrium that has persisted throughout the history of our solar system. So there you have it. Jupiter isn't just big, it's not even just impossibly, mind-bendingly massive. Jupiter is the cosmic architect that built the very solar system we call home. Every drop of water in our oceans, every breath of air in our atmosphere, every delicate condition that allows life to flourish on our pale blue dot exists because a giant world spinning in the outer darkness has been conducting a gravitational symphony for over 4 billion years. Tonight, when you look up at that wandering star moving slowly against the background of fixed points of light, remember that you're not just looking at another planet, you're looking at the reason we exist at all. I wish you a very good night. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow, as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.